Before electricity, night arrived like a hard boundary. People stretched their days with candles, oil lamps, and later gaslight, but every option carried a price. Light had to be bought, carried, stored, and watched. A longer evening meant more fuel, and fuel meant money. Most families rationed it not out of habit but necessity. Darkness did not simply happen, it was managed minute by minute. That management came with risk. Open flames sat close to curtains, papers, and wooden walls. A tipped lamp or an unnoticed draught turned light into disaster fast, and whole blocks sometimes paid the cost. Smoke and soot dirtied rooms and lungs, and weak light distorted judgment. People stumbled, misread labels, and missed hazards on stairs and streets. The dark stayed dangerous. Even when it was lit, it only hid less. Gaslight widened what was possible, especially in wealthy districts and busy streets, but it created new limits. Pipes leaked, flames consumed oxygen, and fixtures demanded maintenance that many towns could not afford. Outside the reach of gas lines, the old fuels still ruled, so the night stayed uneven. Bright in a few places, dim in most, and truly black beyond. After sunset, work slowed, travel shortened, and decisions were shaped by one simple fact: light ran out. In the early 1800s, a different kind of light appeared in experiments. It did not come from burning fuel. It came from electricity. When researchers pushed current through two carbon rods set close together, the air between them flashed into a fierce white arc. It looked like daylight. It proved a simple point with huge consequences. Electricity could make light, and it could do it brilliantly. This breakthrough carried a catch. The arc did not behave like a calm, steady flame. It hissed and flickered. The carbon tips burned away, so the gap changed constantly, and someone had to adjust it to keep the light going. The equipment demanded heavy batteries or early generators, and it ran hot and harsh. Electric light existed, but it still belonged to controlled demonstrations, not everyday life. Even with those limits, arc lamps escaped the laboratory in small, strategic ways. They appeared in a few public spaces where the brightness mattered more than comfort or cost, places like streets, large halls, and industrial sites. The effect was undeniable. A single lamp could outshine many gas jets, but the same fact blocked wider use. If electric light needed constant attention and specialized power, it could not yet spread into ordinary homes. After the harsh glare of arc lighting, inventors chased something quieter and more personal. A small light that could sit indoors, steady and safe. The idea sounded simple. Heat a thin piece of material until it glowed. But in open air, that glowing strip behaved like anything in a fire. It oxidized fast and vanished. So experimenters turned to glass bulbs and pulled the air out. An evacuated bulb changed the rules. With less oxygen inside, the hot material did not burn the same way, and the light lasted longer than a bare wire. That felt like progress, and it was. But the victory never held. Even in a partial vacuum, the filament still broke down. It either burned from leftover gases, or it simply overheated and snapped. Minutes of light still counted as failure. This was the new center of the struggle. The bulb itself was no longer the mystery. The filament was. It had to survive intense heat, stay thin enough to glow, and resist crumbling hour after hour. Every test pushed inventors into the same corner. Materials science, not just electricity. Different metals warped, carbon charred. Each attempt proved the concept again, and each attempt ended the same way. Darkness returned. Incandescent light only had one job: keep a thin filament hot enough to glow. But air inside the bulb kept attacking it. Even with a vacuum, the earliest filaments still failed fast. So the race narrowed to two connected problems. One was the material itself. The other was the emptiness around it. If either one was wrong, the lamp lasted minutes. That made it interesting, but not useful. Experimenters began carbonizing ordinary things, paper, cotton thread, wood splints, then shaping the blackened strands into delicate loops. Carbon handled heat better than bare metal and, in a good vacuum, it resisted immediate destruction. Results improved, but inconsistency haunted every test. One filament glowed for a while, the next snapped or crumbled. At the same time, vacuum pumps improved. Each step removed more gas and each step bought more time. Those extra hours changed everything. A lamp that survived a whole evening stopped being a trick and started looking like a product. Longer life meant less maintenance, fewer blackened bulbs, and a more stable light output. It also exposed a new reality. The bulb had to be repeatable, not lucky. The work shifted from proving light was possible to proving it could be made the same way, over and over, at a reasonable cost. By the late 1870s, the problem changed. It was no longer just how to make a filament glow. It was how to make electric light into a product people could buy and rely on. Thomas Edison pushed hard toward that goal, building a lamp that lasted long enough to be sold and used daily. In Britain, Joseph Swan reached similar results, and separate workshops also chased the same prize. The race moved from experiments to business. But a bulb alone did not solve darkness. If a lamp failed or flickered or broke after a week, customers blamed the whole idea of electric light. So Edison and others treated lighting as a full service. The lamp, the socket, the wiring, the switches, and the way power fed the system. They tested parts together, not in isolation, because one weak link ruined everything. The product stopped being a single invention. It became a package. This was the real commercialization leap. Companies did not just sell glass bulbs. They sold the promise of dependable indoor light, night after night. Demonstrations turned into contracts. Workshops turned into factories. Patents turned into competing brands, each claiming a safer, longer-lasting, more practical system. Edison's group and Swan's supporters fought for customers and markets, and the question shifted again. Not whether electric light worked, but how fast it could spread. Electric light stopped being just a product and became a service. A single building could run a generator, but that model hit a wall fast. It cost too much, it demanded constant attention, and it only helped whoever owned the machine. The next step changed the scale completely. Electricity came from a central station, then travelled outward through wires. One engine room served many streets. That shift created a new problem. Once power flowed beyond one property, every connection mattered. Wires had to survive weather, heat, and accidents. Insulation and fuses stopped being optional extras and became the difference between light and fire. And because customers plugged into the same network, the system had to behave predictably. If the voltage wandered or the current surged, lamps failed and trust collapsed. So electric lighting forced agreement. Utilities and manufacturers pushed towards standard voltages so lamps worked the same from one block to the next. Sockets became standardized so a bulb fit without improvisation. Switches, meters, and safety rules followed because strangers now shared the same hidden energy. The milestone was not only brighter nights, it was a grid that turned lighting from a local trick into a scalable public utility. By the late 1880s, electric light faced a new limit. Power did not travel far. The early networks worked best when the power station sat close to the customers because the electricity weakened over distance and the wires grew hot and wasteful. That meant bright new lighting often stayed packed into a small downtown zone. It looked modern, but it did not spread easily. Then a different approach gained force. Instead of pushing one steady kind of current, engineers used alternating current, or AC, which changed direction many times a second. The breakthrough came with transformers. These devices raised voltage to send electricity over long distances with less loss, then lowered it again near homes and shops so lamps could run safely. Distance stopped being the enemy. Power could leave the city centre and keep its strength, and that set up a fight. This struggle became known as the War of Currents. Competing systems, competing business models, and competing ideas of safety and control. It mattered because it decided how the grid grew. With AC and transformers, one plant could serve far more people, reaching outward along roads and rail lines and into new neighbourhoods. Electric light no longer depended on being near the generator. It became something suburbs and smaller towns could realistically adopt. By the early 1900s, incandescent light still carried a stubborn weakness. The familiar carbon filament wasted energy as heat and slowly evaporated, darkening the glass and dying too soon. Engineers needed a filament that could run hotter without collapsing. They found it in tungsten, a metal with a melting point so high it changed the rules. It could glow whiter, longer, and with less electricity. The bulb finally started to grow up. But tungsten brought a new problem. When it ran hot, atoms still boiled off the filament, just more slowly, and that still meant gradual thinning and failure. The next step sounded simple and turned out to be decisive. They stopped treating the bulb like an empty space. Instead of a hard vacuum, manufacturers filled it with inert gases like argon and nitrogen. The gas reduced evaporation and let the filament burn brighter without burning out. Those two changes worked together like a lock and a key. Tungsten delivered the strength to run at higher temperatures, and inert gas made that strength last. Efficiency climbed, lifespans stretched. Bulbs tolerated everyday use without constant replacement, and they produced more light for each unit of power flowing through the wire. That shifted the economics of lighting. Electric light stopped feeling like a fragile upgrade and started becoming the default choice for millions. Once electric light stopped being rare and became routine, cities changed their schedule. Streets that had gone quiet after sunset stayed active because people could see where they walked and what they bought. Shops kept doors open longer, and entertainment stretched later into the night. Darkness lost its power to end the day. It no longer decided when people should stop moving and start waiting. Inside factories, bright lamps rewrote the meaning of a shift. Work no longer depended on windows or the season, and owners pushed production deeper into the evening. In homes, a single switch replaced the rituals of trimming wicks and guarding flames, and families used the extra hours for reading, sewing, and study. Electric light also became a tool for selling. Signs and displays pulled attention in ways print never had. Public officials treated lighting as a safety measure because a lit corner reduced hiding places and made patrols more effective. Accidents fell where steps, crossings, and machinery became easier to judge, but the new brightness carried a cost. Glare blinded drivers and annoyed residents, and some people complained that nights felt washed out. Even early on, observers noticed that the stars faded above growing towns, and they worried the dark itself had started to disappear. By the time the story reached the present, the bulb no longer needed a fragile filament at all. LEDs turned electricity directly into light with far less wasted heat, and they lasted for years instead of weeks. Light became something people could scatter everywhere without thinking about the cost. Streets, signs, phones, cars, and kitchens all carried their own steady glow. Night still arrived. Darkness did not get the final say. Control also changed. Light did not just switch on and off anymore, it adjusted. Smart systems dimmed automatically, shifted color through the day, and responded to motion, schedules, and sensors. A single building could cut power use without returning to shadow, and entire cities could tune brightness block by block. The promise sounded simple: the right amount of light, only where it was needed. The consequence was bigger. Light became managed like data. Underneath it all, vast grids carried power across regions and borders, making cheap, dependable illumination feel ordinary. When storms or failures hit, the sudden dark felt abnormal, almost shocking, because so much work and safety depended on constant light. That contrast completed the long battle. The nights that once relied on flame, smoke, and risk now stayed bright with a tap or a timer. The old limits from the beginning had not just eased, they had vanished.